In this video, we're going to discuss what Euler equations are. So Euler equations have the form I'll put it here, a t squared y double prime t plus bt y prime t plus c y t equals 0. And these equations, these Euler equations, are also called the Cauchy-Euler equation or equidimensional equation. Here, A, B, and C are constants. Okay? Elements. They're all constants. But this is a rare example of an equation with non-constant coefficients. So non-constant coefficients, so this term is a non-constant coefficient and this term is a non-constant coefficient. So we can rewrite, we can say that a2t is at squared, and we can say that a1t is bt. All right? And this is a rare case of having an equation with non-constant coefficients, but we are still able to determine a method for solving that equation. So, how do we solve this equation? How do we solve this equation? Well, we have to make a substitution. X equals ln t. And now we're going to have to use the chain rule for this. So let me remind you, or let's go over what's happening in this equation. So we know that y is in terms of t, right? And we also know that x is also in terms of t. Okay? So by the chain rule, oh, actually, wait up. Y is dependent, let's say that y is dependent upon x, and then x is dependent upon t. And this x right here, I should be more specific, is xt. Okay? And so by this substitution, this substitution right here, this chain rule is not for this. So this is, we're defining a new operation, a new intermediate step between x and t, such that the t squared in A2 and the t in A1 is no longer there, and it's just some constant. That's what we're trying to do. So as a result, by the chain rule, we can say that dy dt is equal to dy over dx, and dx is an intermediate, so we can say that dx is, and then we can multiply that by dx over dt. So based on that, this is our chain rule. Now we know what xt is. Okay, so we know what dx dt technically is. So let me move this to the side as far as it can go. So let's take pink. So we know that xt is equal to ln t, right? And so if we take dx dt, if we take the derivative, then we get 1 over ln t. So therefore dx dt, we can just replace dx dt, we can literally just replace and say that this is 1 over t. So dy dt is equal to dy dx times 1 over t. And then again by the chain rule, again, because so the reason why I'm finding dy dt, by the way, is because dy dt is equivalent to y prime t, and y prime t is this guy, right? So the way we define this was the work of probably some genius mathematician, and what he thought of was like, okay, I know the derivative of ln is 1 over t, or 1 over whatever the argument is, right? So based on that is really convenient, because if I have the derivative of that ln function, then I'm going to get 1 over that, 1 over t, or 1 over however you define it. So based on that, when I substitute this back into here, this 1 over t that we just put here as dx dt cancels out with this other t in a1t. So then a1t just becomes b. So that's really good. That's really convenient. Now we need to do the same for y double prime t. Y double prime t. So y double prime t will be the derivative of dy dt. So it's the derivative of this thing, of dy dx times 1 over t, like so. And then what we can do is we can rewrite this again, and then we get y prime t. Why did I change colors? Y double prime t becomes let's see, negative 1 over t squared, or sorry, if we do the product rule, then we get d2y dx squared, and then 1 over t squared, yeah, and then minus dy dx 1 over t. Okay, and this is just by the product rule. And so if we plug all this in, plug into the Euler equation, so if we plug this into the Euler equation, which I'm not going to do now, then what you end up with is something quite spectacular, because what you end up with is a y double prime x plus b minus a y prime x plus c yx equals 0. And remember, x equals ln t. So this is how we will solve all Euler equations from now on. Okay, so this is what you have to do. You first you identify that your equation has this form: a t squared y double prime t plus bt y prime t plus cyt equals 0. And then you say, okay, I'm going to identify a, b, and c. And then once I've identified a, b, and c, all I can do is I can just plug this into here, and then I can plug a into here, I can plug b minus a into here, I can plug c into here. And then I can solve it. I can solve this equation. You can solve this equation, solve this, as just a constant coefficient, as a constant coefficient second order linear differential equation. And I stole this mind map that I made from when we talked about constant coefficient homogeneous second order linear differential equations. And remember, we ended up with three cases: case A, B, and C. So this again will be used in Euler equations, and you can see that Euler equations are an extension of just constant coefficient homogeneous second order linear differential equations, as we just transform them into a homogeneous equation, right? This goes from Euler to homogeneous. You solve it as a homogeneous, and then the problem will be that the solution won't be in terms of yt, it'll be in terms of yx as something. So let's say yx equals x to the x, yx equals e to the x, right? So then what will happen is we don't want to leave it in terms of x, so we sub in t again, so then yt becomes e to the ln t, and then this just becomes t. So that's just an example. So that's like the last step you always have to do with Euler equations, is you have to plug x equals ln t, plug that substitution back into the equation to make sure that your solution is in terms of t and not x. Alright, so now let's solve this problem. So, like always, please go ahead and try this problem out on your own. Okay, I'm hoping that you've tried it out on your own, and now we're going to begin solving it. So, first thing we have to do is we have to identify that this is indeed a Euler equation. An Euler equation will have the form a t squared y double prime t plus b t y prime t plus c y t equals 0. All right, and then we do our substitution, or at least we pretend like we just substitute x equals ln t. So once we plug that in, what we'll end up with is a y double prime x plus b minus a y prime x plus c y x equals 0. And now we just have to solve this as a homogeneous equation. So if we plug in the values, what we'll end up with is 2 y double prime x and 3 minus 2, which is 1, y prime x minus c, so c is just 1, or plus c, and c is just negative 1, c y x equals 0. And then we can put this into the characteristic equation, which is 2r squared plus r minus 1 equals 0. And then from here we can use the quadratic formula, which is r equals minus b plus minus b squared minus 4ac over 2a. And so what that gives is minus 1 plus minus 1 minus 4 to negative 1. And so as you can see, this is a case A because b squared minus 4ac is greater than 0. Okay, so this is a case A. So we're going to have two real roots. Okay, two real roots. And if this I literally borrowed this from the map that I made. which is up here. But now notice that this is saying that the fundamental set is in terms of t. This is not in terms of t. This will be in terms of x. We will have to convert it to t later. So then, anyways, 2 over 2a, which is 4. And so then r equals minus 1/4 plus minus, and the inside of this radical simplifies such that it is 1 plus 8, and then that is root 9, and that's 3. So 3 over 4. So R1 is negative 1/4 minus 3/4, which is negative 1. And R2 is negative 1/4 plus 3/4, which is 1/2. So therefore your fundamental set is e to the minus x and e to the 1/2 x. And that's your fundamental set. And so then your general solution in terms of x is yx is equal to c1 e to the minus x plus c2 e to the 1/2 x. And so remember that our equation was in terms of t, so we should have our solution in terms of t as well. So x is just an intermediate step, right? So x, here we can write this, x equals ln t, and so then we can say yt is c1 e to the minus ln t plus c2 e to the 1/2 ln t. And so then yt is equal to c1, actually it should be more clear, c1, we bring the constant in here, same thing with this, so e to the ln of t to the minus 1 plus c2 e to the ln t 1/2, and whatever is the argument of ln in a e to the ln is simplified to just that argument. So that's just c1 t times t to the minus 1, c2 t to the 1/2, and this is the value of yt. So there you go. That is your general solution in terms of t. That is how you should be expressing your solutions. Next problem. So like always, please go ahead and try this problem out on your own. So I'm going to go a bit faster now, and I'm going to, and hopefully you guys catch on. So let's write the equation in terms of x. So equation in terms of x is a y double prime. Whoops. So a double prime. So this a is 1 here, right? And b is 1 as well, and c is also 1. With that in mind, let's fill in this equation. B minus a y prime x plus c yx equals 0. So a is 1, so this is just y double prime x, and b minus a is 0, so we don't need that. So c, and then c is just 1, so this is y prime double prime x, yx equals 0. Now if we put in this into the characteristic equation, we get r squared plus 1 is equal to 0. And this does not have any real solutions, so this must have some complex solutions. So r equals minus 1, or sorry, r squared equals minus 1, r equals minus 1, and plus minus. So therefore r equals 0 plus minus I. And so as you can see that when this is a case C, right? Because you can have R1 as 0 plus I, and you can have R2 as 0 minus I. So there you go. Those are your two complex solutions, or your two complex roots. And this is a case C. So the general solution and the fundamental set will look like this, except now, because we have done the substitution, it is no longer in terms of t, but it is now in terms of x. It is now in terms of x. Mu x. So everything gets changed. Everything gets changed to just x. Okay? So then, as a result, remember that r is equal to lambda I mu. So lambda and mu. So your fundamental set, is such that lambda is 0, right? So e to the power of 0 is always just 1. So these are just 1. Okay? So then your fundamental set is cosine mu x. So mu in this case is 1, right? So this is cosine x sine x. And then therefore your general solution in terms of x is yx c1 cosine x plus c2 sine x. And so therefore that is your yx, but now we need to substitute with x equals ln t. So therefore yt is equivalent to c1 cosine ln t plus c2 sine ln t. And that is your general solution expressed in terms of t. There you go. All right, I got one last problem for you guys, and then we'll call it a day. So, again, identify A, B, and C. So actually, please, go ahead, pause this video, and try this last example out on your own. Okay, I'm assuming you've come back, and now let's get to it. So first thing we got to do is we got to identify the constants. So A is 1, B is -1, and oh, wait a minute. This is not in the form of an Euler equation. So let's make it into the form of an Euler equation by multiplying everything by t, right? Because the Euler equation it looks like this. Euler equation looks like this. So let me borrow that. Right? Euler equation is supposed to look like this. So what we have to do is we have to multiply everything by t. So that's y double prime t minus t y prime t plus 5yt equals 0. So as a result, A is 1, B is -1, C is 5. From here, we can put this into the substituted equation, where the substitution was xt equals ln t. Okay, and I should probably change the color to yellow. So a y double prime x plus b minus a y prime x plus c y x equals 0. So a is just 1. So this is y double prime x, and then b is -1 and a is 1. So then this must be -2 y prime x, and c is 5. So there you go. So if we put this into the characteristic equation, you get r squared minus 2r plus 5 equals 0. And again, if we put this into the quadratic formula, r equals minus b plus minus radical b squared minus 4ac over 2a. So then minus b is 2 plus minus b squared is 4 minus 4 times 1 times 5 over 2. And so as you can see, b squared minus 4ac is less than 0. So we're going to have two complex roots. This is a case C. Case C. Wait, case C. Like that. So then therefore we have to let's go to our map. And look, case C, this was everything we knew about that. So this r needs to be changed, and this r, so we can rewrite this r as 2 over 2, which is 1 plus minus plus minus 4 minus 20, which is minus 16 over 2, and then 1 plus minus I, and then 4 over 2 is 2. That is the value of your r. All right, and so therefore this your lambda is 1 and your mu is 2. Okay, and so here, if I should put a box around this. There you go. So we know what lambda and mu are. So as a result, we can get our fundamental set. Our fundamental set, which is going to be in terms of x and not t. So this is going to be e to the x cosine 2t, e to the x sine 2t, like so. And then that is your fundamental set. And then your general solution in terms of x is going to look like this. Not set, solution is going to look like this. This is yx, and I'm going to change colors. Yx is equal to c1 e to the x cosine 2. I just realized this should be x. This is the thing about Euler equations, man. You gotta know that you're either an x or t. So make sure you know that. Do your practice. C1 e to the x cosine 2x plus C2 e to the x sine 2x. That is your general solution in terms of x. Now remember, x equals ln t. So therefore yt is going to look like this. Yt c1 e to the ln t cosine 2 ln t c2 e to the ln t sine 2 ln t. And so c1, and so whatever is e to the ln, whatever the argument of ln is, that is the argument itself simplified. And then cosine of ln t squared, right? Because I just brought this 2 in. C2 again, t sine to the, I'm going to bring this t in again, or this 2 again into the argument. So there you go. this is your yt. This is your yt expressed as that.